Hello and welcome to Diplomatic Derivatives. In today's video, we're going to talk about the number theory. Now, the main concept in number theory is the Euclidean algorithm that we're going to deal with. The reason is because it's going to help us solve theorems in group theory, most importantly, the cyclic group theorems for now. And the concept which follows the Euclidean algorithm is the next concept, which is the Bizot's identity, that will be tackled in the next video. So for now, we're going to see what is the Euclidean algorithm. So the Euclidean algorithm is a simple and efficient method for finding the greatest common divisor of two integers. That is, the largest number that divides both numbers exactly. Now let's suppose you have two numbers. You will first, and if someone asks you to write the divisors of those two numbers, what is the process that you do? You will write each divisor by seeing that this number goes in which table, right? So for example, if you have 6, you know the divisors are 1, 2, 3, and 6, right? 6 is a small number, so it was easier for you to do it in a matter of seconds. But what if you have large numbers? It will take time. It's a time-consuming process, and it will take some time for you to understand, to write each and every divisor. Let alone the divisor of the next number as well, and then finding the greatest common of those two numbers, right? So the process which is using a Euclidean algorithm is a simple one and time-saving, efficient method to find the GCD. Okay, so let's suppose you have 84. In this way, you write all the divisors, right? Being 1, 2, 3, 4, 6, 7, 12, 14, 21, 28, 42, and 84. Next, you have 30, 1, 2, 3, 5, 6, 10, 15, 30. So you have to find in each table whether 14 goes, whether 84 goes in 14, it goes in 21, 28, 42, and then it will take time, and then you will write all of these, and then you will see which is the greatest common divisor, here being 6. 6 is the common and the greatest one. Other than 6, there is nothing else after which is common, right? So 6 becomes the greatest common divisor. But now we will be seeing a process by which we will be able to do it in a matter of seconds. How? Suppose you want to find GCD AB where A is greater than B. Now make sure that the two numbers that you have, you keep A as the bigger number and B as the smaller number, and you find GCD for that. How do we do that? You divide A by B and write it like A is equal to B dot Q plus R. Now Q and R are the quotient and remainder. This is the main formula, which is A is equal to B dot Q plus R. We'll take a look at it with an example. We take the same numbers, 84 and 30, right? So 84 is A and 30 is B. So how do you write it? You write 84 here and then 30 comes here. So basically the reason why we're saying A should be greater than B is that we are going to divide A by B. So you divide it, you write 84 inside and you write 30 outside. Okay, you divide it, therefore you get a quotient and you get a remainder, right? This quotient is going to be written, in this case it is 2. So 32s are 60, 60 comes here, 33s are 90, so 90 is greater, therefore you can use that. So you take 2, this 2 comes here and the remainder becomes 24. Okay, so this is how you write the first step. You write A is equal to B dot Q plus R. Now the second step is the same formula, but only the values of A and B are going to change. How? We see that. What happens is B over here now becomes A, okay, and this R over here now becomes B. How? We see here. So what you see here in this step is this 30, which was B, is now coming in the position of A, and this R, which was 24, is now coming in the position of B over here. Okay, so R becomes B and B becomes A. All right, and in this way now you have the next statement. So again, now since B became A, again you are going to see that A is greater than B. So you will divide A divided by B, you get 24, 30 inside, and what you get here is 30, which comes inside, and outside you have 24. So 24 ones are 24, okay, and you get the remainder as 6, right? So this 6 comes over here and remainder 1, quotient 1 comes over here. All right, Now the same step is going to continue. So the values of A and B are going to change. Rest, the process remains the same. So now 24 comes here and 6 comes here. So now this is A and this is B. Okay, so this is 24 here as A and remainder becomes B. Now 6 and 24 also get divided. So 24 by 6, 6 4s are 24, 4 is the quotient and the remainder is 0. Now you have to continue until the remainder is 0. This process continues if you have even bigger numbers. For example, if you have bigger numbers than these, you will have more steps, right? You don't get the remainder in just 3 steps. Here in this case, you get the remainder as 0. In just 3 steps, you get the remainder 0. And once you get the remainder as 0, it means that the step which was before this step, okay, which is this step over here, the remainder of this step is the answer, which is GCD. Okay, so the step where you're getting 0, you have to go to the previous step to find the GCD, which is a remainder of that second last step. All right, that's how you find the value of GCD. This is the greatest common divisor of the two numbers. All right, that's the process. The only thing you have to remember is the formula, which is A is equal to B dot Q plus R. A is greater than B. So you divide A by B, you get a formula, which is this, right? Then B becomes A and R becomes B. So A and B values are only changing in this manner. Okay, again A and B, A is greater than B, again divide, you get remainder and quotient. Again you have to write, you have to keep on doing this process until you get the remainder as 0. Once you get that, the answer is the GCD is in the second last step, which is here. In this case it is 6. All right, that's the way to perform the Euclidean algorithm. Now, why does it matter? Why is Euclidean algorithm so important? Number one, it's fast. So for bigger numbers, it is not time consuming at all. You can do it for like in a matter of seconds. Once you know the formula, once you get the hang of it, it's a very easy way to perform this algorithm, and you'll be able to find the GCD in a matter of seconds. So it's very easy to perform for larger numbers. Used in cryptography, modular arithmetic, and group theory. The group theory is very important here because we are going to use this Euclidean algorithm in the group theory for performing certain proofs of theorems, and it's the foundation for Bizot's identity. Now this Bizot's identity is the next concept that we're going to tackle, and it will use the values from the Euclidean algorithm in the Bizot's identity to solve the Bizot's identity, which is also going to be used in the group theory. All right, so that's it for this video. I hope you liked it. I hope the concepts were made easier and clearer, and if you have any questions, you can type them down in the comment box below. Make sure you like, share, and subscribe to my videos so that I'll be able to bring such concepts towards you in the most simpler manner as possible. Next is going to be Bizot's identity. I hope you liked it. Make sure you stay tuned for the next one. Take care. Bye bye.